Why is the thin planar antenna performing better than the thick copper wire design? Today we will find out. What is the advantage of a wide planar structure in high-frequency technology? Today's findings are sort of generic, so this video is certainly interesting for everybody dealing with high frequency. In previous episodes we experimented with loop antennas. We found that a planar design worked better than the one made from thick wire. Actually, I just wanted to find a way to produce the antenna physically more precise using a planar design. I found that this makes sense, however it only partially explains why it works better. So there must be other effects with the planar design that improve the properties of the antenna. Now let's imagine that we excite a vertical and a horizontal electromagnetic resonance oscillation on this structure. You know from earlier episodes, that's the clue in the working principle of this antenna. The electrical length of the loop is crucial for the two resonance frequencies. Therefore, the length should be exactly the same for both resonance modes. When comparing the wire antenna with this planar structure, we already suspect that the latter has a more precise symmetry. By the way, an exact computation of this effect would be complex, so we're just going for a simple qualitative analysis. In the case of the planar antenna, both the outer and inner radius are constant over the entire circumference. In the case of the antenna made from wire, the inner radius is varying. We can assume that the resonance frequencies of the two orthogonal oscillation modes are likely to be closer together when using the planar solution instead of the wire antenna. This finally improves the filter effect and also the antenna matching. Then we have another very interesting effect that we can even quantify. The Q factor of a filter becomes better the lower the electrical resistance of the material used. Q is defined by the ratio of energy stored in the system to the energy lost with each oscillation. We can calculate this from the ratio of the reactance to the ohmic resistance. I constructed the loop of the 866 MHz antenna from thick wire and from relatively wide band, speculating on a good Q factor. And now we will quantify Q. The results of this calculation will be a bit surprising. First of all, we need to know that due to the so-called skin effect, the penetration depth of high-frequency currents at this frequency is only about 2 micrometers. Let's consider this now for the two antenna designs. Physically, the wire actually has a much larger cross-sectional area than the planar conductor, which is only 0.1 mm thin foil. However, with only 2 micrometers current penetration depth, things are getting very different. We can calculate an effective cross-section considering the skin effect. I calculated this with Excel. At just 2 square millimeters, the planar conductor has a significantly smaller physical cross-section than the wire at 6 square millimeters. However, the entire physical cross-sectional area would only be effective with direct current. The effective conductor cross-section at 866 MHz is significantly smaller than the physical cross-section for both designs. And the relation is now even reversed. The planar conductor now has a significantly larger effective cross-section than the round conductor, which results in a significantly smaller ohmic resistance. Here I've calculated the resistances for the material copper and aluminum. Obviously, we can achieve a significantly lower ohmic resistance with a thin foil instead of a thick wire, even if we used less conductive aluminum instead of copper. We are now calculating the Q factor using the example of the copper antenna. The reactance equals 2 times pi times the frequency times the inductance of our loop. The inductance of the loop, which I computed using an online calculator, is about 141 nanohenry. Using that result, we can now easily calculate the reactance of the loop and the Q factor. The Q factor of the wire antenna is 15.8 and the Q factor of the planar antenna is 74.0. In fact, the planar antenna is having a significantly higher Q factor than the wire antenna. That's a bit surprising, isn't it? Well, you could get smarter every day if you subscribe to the channel. The reflection measurement shows really good results. I have rarely seen such a good antenna matching. The VSWR is almost equal to 1 at the center frequency and the reflection loss is correspondingly high. And then you can see the effect of the band filter very nicely. The skin effect is always an important issue in high-frequency technology. But not always, only at radio frequencies. It can certainly become relevant in the low-frequency range when you have high currents and therefore need thick conductors. If the thickness of the conductor is several millimeters, then the skin depth has an effect even at low frequencies. In order to achieve good conductivity at high frequencies, you need a big surface of conducting material. The physical cross-section of the conductor is practically not relevant. It can be even hollow inside. I hope you were able to take something away from my example. See you next time. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.